The camera that's been switched off for 36 years is still, right now, arguably the most talked about camera in the history of space exploration, because what it captured before NASA finally shut it down forever might be the most important photograph anyone has ever taken of anything. Stick around, because I'm about to walk you through the actual story behind Voyager 1's most incredible images, why the spacecraft that took them is now down to its last flickering scraps of power, and why 2026 might be remembered as the year this whole legendary mission finally starts running out of road. And if you want more real space stories built from actual mission data instead of recycled hype, subscribe now, because there's a lot more of this coming. Let's go back to where this entire story actually begins, because almost 50 years later, it's still hard to believe this mission was ever approved in the first place. In the summer of 1977, NASA launched two nearly identical spacecraft within weeks of each other, Voyager 1 and Voyager 2, both riding a genuinely rare planetary alignment that only happens once every 176 years, one that let a single trajectory swing past Jupiter, Saturn, Uranus, and Neptune, using each planet's own gravity to slingshot toward the next. Voyager 2 took the long route through all four giant planets. Voyager 1 took a faster, more direct path built specifically to fly close past Saturn's massive moon Titan, sacrificing any chance of visiting Uranus or Neptune in exchange for the best possible look at that one target. Each spacecraft carried a suite of 10 scientific instruments and a single imaging system built around two cameras, a wide angle and a narrow angle, technology that would look laughably primitive by today's phone camera standards, yet somehow still managed to produce some of the most important photographs in the history of the species. The first major stop was Jupiter in March of 1979, and this is where Voyager 1 immediately started rewriting the textbooks. Scientists already knew Jupiter had a great red spot, a massive swirling storm visible even through ground-based telescopes, but nobody had ever seen it in genuine detail until Voyager's cameras got close enough to reveal it as an enormous churning storm system wider than Earth itself, with visible internal structure and turbulent edges where it collided with neighboring cloud bands. Then came the detail that genuinely stunned the mission team. While analyzing images of Jupiter's moon Io, a NASA engineer named Linda Morabito was studying a routine navigation image, checking star positions to help pinpoint the spacecraft's exact location, when she noticed something strange curving off the edge of the moon's disk. At first, it looked like an image artifact, maybe an error in the data. It wasn't. It was an active volcanic plume rising more than 150 miles above Io's surface, the first time in history active volcanic activity had ever been directly observed anywhere beyond Earth. Nobody on the mission team had expected that. Io was assumed to be a cold, dead, cratered rock, similar to our own moon. Instead, Voyager had accidentally caught it in the middle of erupting, and follow-up images confirmed multiple simultaneous eruptions happening across the moon's surface, a level of volcanic activity that turned out to be more intense than anywhere else in the entire solar system, Earth included. Comment below if you've heard this story before, because honestly, the fact that one of the biggest planetary discoveries of the 20th century was found, almost by accident, buried inside a routine calibration image, is one of those details that tends to surprise people every time. From Jupiter, Voyager 1 pressed on towards Saturn, arriving in November of 1980, and this is where the mission delivered its second irreplaceable stop, because remember, Voyager 1's trajectory was deliberately built around a single close flyby of Titan, Saturn's largest moon, and one that scientists suspected might have its own thick atmosphere. It did. Voyager 1's instruments confirmed Titan was wrapped in a dense, hazy nitrogen atmosphere thicker than Earth's own, so opaque that the cameras couldn't see through it to the surface underneath at all. That single flyby effectively defined Titan as one of the most scientifically important moons in the solar system for the following 4 decades, eventually leading directly to the Cassini-Huygens mission, landing a probe on its surface more than 20 years later. But getting that close look at Titan came with a permanent cost. The specific trajectory needed to fly close enough to study Titan's atmosphere bent Voyager 1's path up and out of the plane where all the planets orbit the Sun, permanently ending any chance the spacecraft ever had of visiting Uranus or Neptune. From that point forward, Voyager 1 was headed only one direction, up and out, away from the solar system entirely, forever. Along the way past Saturn, the cameras also captured detailed images of the planet's rings, revealing structure nobody had properly resolved before. Thousands of individual ringlets, faint braided strands, and gaps carved out by small embedded moons, transforming what ground telescopes had shown as a handful of broad bands into an almost impossibly intricate structure. And then, once that final planetary encounter was complete, NASA made an unusual decision. Rather than immediately shutting down the spacecraft's imaging system, which had already accomplished its main scientific goals. Mission scientist Carl Sagan pushed for one more use of the cameras before Voyager 1 permanently retired them. And this is where the story gets genuinely emotional if you actually sit with it. In February of 1990, from roughly 3.7 billion miles away, well beyond the orbit of Neptune, Voyager 1 turned its camera back around and took a series of 60 images capturing the entire solar system in a single mosaic. Inside one of those frames, Earth appeared as a single pale blue point of light, less than a pixel across, suspended in a scattered beam of sunlight caught inside the camera's optics almost by accident. Sagan later described it as a pale blue dot, a phrase that became the title of his 1994 book, and one of the most quoted reflections on humanity's place in the universe ever written, built around the idea that everyone who has ever lived, every war, every celebration, every single human life, played out on that one barely visible speck of light. Immediately after capturing that mosaic, mission controllers permanently shut down Voyager 1's cameras. Not because anything broke, it was a deliberate decision, made to save the spacecraft's dwindling power for instruments that could still return meaningful scientific data as it continued outward, since there was nothing left out there bright enough or close enough for the cameras to usefully photograph anyway. That image, taken more than 3 decades ago, remains the last photograph Voyager 1 will ever take, and very likely the most philosophically significant photograph any spacecraft has ever produced. If that story genuinely gets to you the way it gets to me every time I revisit it, drop a like on this video, because there's something about a single accidental beam of light landing on a 2-pixel dot that still hits differently no matter how many times you hear it explained. From there, Voyager 1 kept flying quietly, with no more cameras and steadily fewer working instruments, and in August of 2012, it achieved something no human-made object had ever done before. It crossed the heliopause, the outer boundary where the sun's constant stream of charged particles, the solar wind, finally gets overwhelmed by the thin and gas and radiation drifting between the stars. Voyager 1 became the first spacecraft in history to enter interstellar space, technically still gravitationally bound to our sun, and still many thousands of years away from leaving the solar system's outer edge entirely, but now flying through the space between stars, rather than the space carved out by our own sun's influence. Voyager 2 followed the same milestone 6 years later in 2018, becoming the second spacecraft to make the same crossing. Now here's where the story catches up to right now, to 2026, because this is exactly the part of the mission where things have gotten genuinely urgent. Both Voyager spacecraft run on radioisotope thermoelectric generators, devices that convert heat from the natural radioactive decay of plutonium-238 directly into electricity. There are no solar panels involved at all, since sunlight this far from the sun is far too faint to be useful. At launch, Voyager 1's 3 generators together produced roughly 470 watts of power, enough to comfortably run its full original suite of 10 scientific instruments plus cameras, transmitters, heaters, and everything else on board. But plutonium-238 decays at a fixed, unavoidable rate, and Voyager 1's power output has been quietly shrinking every single year since 1977, currently losing about 4 watts annually. That number sounds small. It is not small. 4 watts is roughly the entire yearly power budget mission engineers now have to work with, meaning every year, something on board has to be sacrificed just to keep the spacecraft's most essential systems warm enough and running long enough to keep talking to Earth. Engineers have been managing this slow, unavoidable decline for years now through a careful, deliberate program of instrument shutdowns, and the pace of those shutdowns has picked up noticeably. In February of 2025, NASA powered down Voyager 1's cosmic ray subsystem, a set of 3 telescopes that had been measuring high-energy particles from the sun and from deeper in the galaxy since launch. Then, on April 17th of this year, engineers at NASA's JET Propulsion Laboratory sent a command to shut down another one, the Low-Energy Charged Particles Experiment, an instrument that had been running nearly continuously for almost 49 straight years, helping scientists understand the structure of the region Voyager 1 is currently flying through. According to NASA's mission team, that specific shutdown alone buys the spacecraft roughly 1 more year of breathing room. And here's a small detail that says a lot about how carefully this decision was made. Rather than switching off that instrument entirely, engineers left a tiny motor running, the one that physically rotates the instrument's sensor to scan different directions, drawing just half a watt of power, purely to prevent it from mechanically seizing up in the cold, on the extremely slim chance that power levels stabilize enough someday to bring it back online. As of right now, Voyager 1 has exactly 2 working science instruments left: the magnetometer, which measures magnetic fields in the interstellar medium, and the plasma wave subsystem, which listens to the density and behavior of charged particles drifting through the space around it. That's it, out of an original suite of 10. NASA's own mission team has stated plainly that these two remaining instruments are still working great, sending back genuinely unique data from a region of space that no other human-made spacecraft has ever explored. But the honest reality is that the list of things still switched on keeps getting shorter, and engineers are now weighing which system gets sacrificed next with the same careful math they've been running for years, matching remaining watts against remaining priorities. There's an even bigger fix in the works too, something the mission team has informally nicknamed the Big Bang. And no, that name isn't describing anything explosive happening to the spacecraft. It refers to a coordinated plan to swap out a whole group of older, power-hungry electrical components all at once for newer, lower-power alternatives, an attempt to squeeze meaningfully more operational life out of both spacecraft's dwindling power budget in a single major overhaul, rather than a slow trickle of individual shutdowns. NASA is testing this procedure first on Voyager 2, since it currently sits closer to Earth and has slightly more spare power to work with, making it the safer spacecraft to experiment on before potentially rolling the same fix out to Voyager 1. And just to put into perspective exactly how far away we're talking about here, as of this year, Voyager 1 sits more than 25 billion kilometers from Earth, something like 16 billion miles. So distant that a radio signal traveling at the literal speed of light takes hours just to make the one-way trip. NASA has stated that on November 18th of this year, Voyager 1 will officially cross the threshold of being one full light day away from Earth, meaning a signal sent from the spacecraft. That day will take a full 24 hours just to arrive back on our planet, and another full day for any response to travel back out to it. Every single command, every scrap of data, every decision about which instrument lives and which one goes dark is happening across a communication delay measured in the better part of 2 full days round trip. Here's what makes all of this worth sitting with for a moment. Voyager 1 isn't failing because anything on board is fundamentally broken. Nearly 50 years after launch, the spacecraft's original hardware, its computers, its thrusters, its transmitter, is still functioning, still following commands, still pointing its antenna precisely enough toward a planet it left behind before most of the people watching this video were even born. The mission isn't ending because of some catastrophic failure. It's ending because of simple, unavoidable physics. A chunk of radioactive plutonium slowly, steadily decaying, exactly the way physics says it has to, 4 watts at a time, every single year, forever, whether anyone on Earth is ready for that or not. Mission engineers have said publicly that their hope is to keep at least one working science instrument running into the 2030s, which would push this mission's active scientific life to somewhere around 60 years after launch, an almost unthinkable stretch of continuous operation for a spacecraft that was originally only guaranteed to survive its initial 4-year planetary tour. Even after science operations eventually stop entirely, both Voyager spacecraft are expected to keep drifting silently outward, carrying their golden records, the pair of phonograph discs loaded with sounds and images meant to represent Earth to any curious travelers who might one day intercept them, for what NASA estimates could be tens of thousands of years or longer before either one comes anywhere close to another star system. Step back and look at the full arc of this thing. Voyager 1 launched during the disco era, using computer technology that had less processing power than a basic calculator you'd find in a desk drawer today. It found active volcanoes erupting on a moon nobody expected to be geologically alive. It revealed Saturn's rings as a staggeringly intricate structure rather than a handful of simple bands. It captured the first spacecraft to fly close enough to confirm a thick, hazy atmosphere wrapped around Titan. And then, almost as an afterthought, on its way out of the solar system entirely, it turned around, one last time, and photographed the entire human story compressed into a single pixel of reflected sunlight, before shutting its own eyes forever and continuing to fly blind through interstellar space for the next 36 years and counting. Now, in 2026, we're watching the final quiet chapter of that story play out in real time, one carefully sacrificed instrument at a time, as a piece of plutonium the size of a grapefruit slowly runs out of the only thing keeping humanity's most distant conversation still going. If stories like this one, built entirely from actual mission data and real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance we're going to be covering whatever comes next for Voyager 1 sooner rather than later. Thanks for watching, and I will see you in the next one.